protocols, you need to understand the basics of computer networking. The more you understand how common networks are built and function, the easier it will be applied to that knowledge to capturing, analyzing, and through this section, I will introduce the basic network concepts and that you will encounter every day when you're analyzing network protocols. I will also lay the groundwork for a way to think about the network protocols, making it easier to find previously unknown security issues during your analysis. So let's get started by the network architecture and protocols here. Network. So this is our topic here that you will learn about. So let's start by reviewing some basic networking terminology and asking the fundamental question: what is a network? So the network is a set of two or more computers connected together to share information, and it's a common to refer to each connected device as a node here. As you can see here, workstation node, mainframe node, server node, and this is our network here. So so it's common to refer to each connected device as a node on the network to make the description applicable to a wide range of devices. Here you are seeing a very simple example of our nodes here. So this the diagram shows three nodes connected with a common network, and each node might have a different operating system or hardware, but as long as each node follows a set of rules or a network protocols, it can communicate with other nodes on the network. So to communicate correctly, all the nodes on a network must understand the same network protocols. Here, let's actually, here. So, and this is the functions and what the network protocols serves in our network here. So, the network protocols serves many functions, including one of these functions here. So this is the maintaining state, session state. So these protocols typically implement mechanisms to create new connections and terminate existing connections. Here this protocol also does identifying nodes through addressing here. So data must be transmitted to correct node on a network. So some protocols implement an addressing mechanism to identify specific nodes or groups of nodes. And we are also going to control the flow. So controlling flow. So this is the amount of data transferred across a network is limited, of course. So the protocols can implement ways of managing data flow to increase throughput and reduce latency. And we are also going to be guaranteeing the order of transmitted data. So many networks do not guarantee that the order in which the data is sent will match the order in which it is received. And a protocol can reorder the data to ensure it's delivered into correct order. And we are also going to detecting and correcting errors here. So many networks are not 100% reliable, right? So data can become corrupted, and it's important to detect the corruption and ideally correct it. And here, lastly, formatting and encoding data. And the data isn't always in a format suitable for transmitting on a network, and the protocol can specify ways of encoding data, such as encoding English text into binary values. The Internet Protocol Suite. TCP/IP is a de facto protocol that modern networks use. Although you can think of the TCP/IP as a single protocol, it's actually a combination of two protocols: the Transmission Control Protocol (TCP) and the Internet Protocol IP. And these two protocols form part of the Internet Protocol Suite, IPS. So this is the Internet Protocol Suite and these diagrams. And I will explain all of these diagrams right now here. So, and this Internet Protocol Suite, this is the conceptual model of how network protocols send network traffic over the internet that breaks down network communication Int4 layer as shown in here. So application layer, transport layer, internet layer, link layer. And Ethernet PPP is link layer, IPv4, IPv6 is internet layer, TCP and UDP is transport layer. Actually, let me add comma here. TCP and UDP is transport layer, HTTP, SMTP, DNS is, and etc. is application layer. And these protocols are more, but this is just most used protocols in Internet Protocol Suite. And these are the external connections here. So the link layer directly connects to physical network, and also physical network connects directly to link layer here. So actually, let me get this here, and here. I will apply the same for user application, right? Here, whether it is a browser or just an online game, this is works like that. So now I will explain Internet Protocol Suite. So let's get started with the link layer. This link layer here. So this layer is the lowest level and describes the physical mechanisms used to transfer information between nodes on a local network. And well-known examples include the Ethernet, both wired and wireless, and the point-to-point protocol PPP. We also have the internet layer here. So this layer provides the mechanisms for addressing network nodes, and unlike in layer 1, the nodes doesn't have to be located on the local network. This level contains the IP. On modern networks, the actual protocol used could be either IP version 4 or IP version 6. And here we also have the transport layer. So this layer is responsible for connections between clients and servers, and sometimes ensuring the correct order of packets and providing service multiplexing. And service multiplexing allows a single node to support multiple different services by assigning a different number for each service, and this number is called the port. So the TCP and user datagram protocol operate on this layer. And we also have the application layer. So this layer contains network protocols such as the Hypertext Transport Protocol, HTTP, which transfers web page contents, and the Simple Mail Transport Protocol, SMTP, which transfers the email, and the Domain Name System Protocol, DNS here, which converts a name to a node on the network. Through this course, we will focus primarily on this layer. Actually, in this section, we will focus primarily on this layer, but in all of our course, we will learn all of these layers and protocols. So see you in next lecture. Each layer here interacts only with the layer above and below it, but there must be some external interaction with the stacks here. So here I draw some diagrams that will show you two external connections, and the link layer interacts with the physical network connections transmitting the data in a physical medium, right? So such as pulses of electricity or light. And the application layer interacts with the other application, and an application is a collection of related functionality that provides a service to a user. And in this figure, you are seeing an example of an application that processes an email. And the service provided by the email application is sending and receiving of messages over a network. And here, typically, applications contains these components, which is the network communication. This component communicates over the network and processes incoming and outgoing data. For a email application, the network communication is most likely a standard protocol such as SMTP, POP3, IMAP, or others. And we also have the content parsers here. Oops, actually we have here content parsers. So data transferred over a network usually contains content that must be extracted and processed. So content might include textual data, such as the body of an email, or it might be pictures or video. And we also have the user interface, and this is the user interface that user interacts to it. So the UI allows the user to view received emails and to create a new emails for transmission. In email application, the UI might display emails using the HTML in a web browser. And then I will also notify you that the user interacting with the UI doesn't have to be a human being. It could be another application that automates the sending and receiving of emails through a command line tool. The PDU, the protocol data unit, in each layer contains the payload data that is being transmitted. And it's a common to prefix a header which contains information required for the payload data to be transmitted, such as the addresses of the source and destination nodes on the network, to the payload data. So sometimes the protocol data unit, PDU, also has a footer here that is suffixed to the payload data and contains values needed to ensure correct transmission, such as error checking information. And here in this diagram, I created how PDUs are laid out in the IPS. Remembering from the previous lectures, IPS means Internet Protocol Suite. Here. So let's get started with the application layer here. So you can see here we have layer 4, we have application, station, internet layer, and the link layer. Now I will explain all of these layers and their payloads, headers, one by one. So the TCP header contains a source and destination port number, which is here, source and destination port number here. And these port numbers allow a single node to have a multiple unique network connections, and port numbers for TCP and UDP range from 0 to 65,535 here. And the most port numbers are assigned as needed to new connections, but some numbers have been given a special assignment, such as the port 80 for HTTP. You can find the current list of assigned port numbers in the etc services file on the most Unix-like operating system, but you can also check in from the Wikipedia from internet. And a TCP payload and header are commonly called a segment, whereas a UDP payload and header are commonly called a datagram. The IP protocol uses a source and destination headers. The destination address allows the data to be sent to a specific node on the network, and the source address allows the receiver of the data to know which node sent the data and allows the receiver to reply to the sender. IPv4 uses 32-bit addresses, which you will typically see written as a 4 numbers separated by dots, such as this: 192.168, 192.168, here 10 and 1. So this is an example IP version for IP address. And IPv6, actually let me notify here, IP version 4. So but the IPv6 here, IPv6 uses 128-bit addresses because 32-bit addresses aren't sufficient for the numbers of nodes on the modern networks. IPv6 addresses are usually written as a hexadecimal number separated by colons, such as, for example, FA80 000 4 times 0 here. Actually, let me increase the size it here 000, and so this is address. Long strings of 4 times 0, as you can see here, we've written like that. Long strings of 000 numbers are collapsed into two columns. For example, if you want to write this IP version 6 number easily, you can also write like that. For example, 1 2 3. So 1 2 3 here. Ethernet also contains source and destination address. Source and destination address. Ethernet uses a 64-bit value called a media access control address, which is typically set during a manufacture of the Ethernet adapter. And you will usually see MAC addresses written as a series of hexadecimal numbers separated by dashes or colons. For example, MAC address writes like this. For example, 0A with dashes. We will separate here 28, 99, 3, A5. So this is an example media access control address. And the Ethernet payload, including the header and footer, is commonly referred as frame. Data transmission. Let's briefly look at how data is transferred from one node to another using the IPS data encapsulation model. In this diagram, you are seeing the simple Ethernet network with the 3 nodes, 1, 2, 2, 3. So here, in this example, the node at here, actually let's name this the Typhoon's computer, and here let's actually make this auxily.com and called, for example, Typhoon's network, right? In our laptop here. So for example, with the IP address 192.168.0.101 named Typhoon's computer wants to send the data using the IP protocol to the node with the IP address here auxily.com, the IP address 192.168.0.108. And the switch device, this is the switch device of us, forwards Ethernet frames between all nodes on the network. The switch doesn't need an IP address because it operates only at the link layer. Actually, remember what link layer is this? This is the layer 1. So the switch device doesn't need an IP address because it operates only at the link layer. And here I will write that down. What takes place to send the data between two nodes. The first step, the operating system. Actually, let me copy this here. Yeah. And make it upper. The first step, step 1. Step 1. The operating system network stack. So, the operating system network stack node encapsulates the application and transport layer data and builds an IP packet with a source address of 192.168.0.101. Because remember, this is the Typhoon's computer IP address. And the destination address, here I wrote that as a 2, the destination address of 192.168.0.108. And the step 2 after that, step 2 is the operating system can, at this point, encapsulate the IP data as an Ethernet frame. Encapsulate IP data as an Ethernet frame. So the operating system can, at this point, as I said, encapsulate IP data as an Ethernet frame, but it might not know the MAC address of the target node, and it can request the MAC address for a particular IP address using the Address Resolution Protocol ARP, which sends a request to all nodes on the network to find that the MAC address for the destination IP address. And the step 3 is once the node at Typhoon's computer receives an address resolution protocol response, it can build the frame, right, as here. So the setting source address to the local MAC address of here 115577FFA1BB and the destination address. So destination address is actually this, and here our address resolution protocol just figured out our Typhoon's computer MAC address and tells us that our source MAC address is Typhoon's computer MAC address and the destination is this. And the step 4 is actually ARP response. Step 3 was ARP response, and the step 4 is that then lastly the switch forwards the frame to the destination node, which unpacks the IP packet and verifies that the destination IP address matches. Then the IP payload is extracted and passes up to the stack to be received by the waiting application. Network routing. Ethernet requires that all nodes to local network. This requirement is a major limitation for a truly global network because it's not practical to physically connect every node to every other node, rather than require that all nodes to be directly connected. The source and destination addresses allow the data to be routed over different networks until the data reaches to the desired destination node, as shown here. In this diagram, we are seeing two Ethernet networks, each with separate IP address ranges. Here, in this lecture, I will explain how the IP uses this model to send the data from the node at one network number 1 to network number 2. The operating system network stack node here encapsulates the application and transport layer data, and it builds an IP packet with a source address of 192.168.0.101 and the destination address of 20.0.1.45. Then, as a step 2, the network stack needs to send an Ethernet frame. But because the destination IP address does not exist on any Ethernet network that the node is connected to, the network stack consults an operating system routing table. In this example, the routing table contains an entry for the IP address 20.0.1.50 or 45. The entry indicates that the router on the IP address 192.168.0.101 knows how to get that destination address. And then the operating system uses ARP, Address Resolution Protocol, to look up the router's MAC address at this 192.168.0.101. And the original IP packet is encapsulated within the Ethernet frame with the MAC address. The router receives the Ethernet frame and unpacks the IP packet. When the router checks the destination IP address, it determines that the IP packet is not designed for the router or destined for the router, but for a different node on another connected network. The router looks up the MAC address of this IP address 20.0.1.45, encapsulates the original IP packet into new Ethernet frame, and sends it onto network number 2. The destination node receives the Ethernet frame, unpacks the IP packet, and processes its contents. And this routing process might be repeated multiple times. For example, if the router was not directly connected to the network containing the node of 20.0.1.45, it will consult its own routing table and determine the next router it could send the IP packet to. Clearly, it would be impractical for every node on the network to know how to get to every other node on the internet. If there is no explicit routing entry for a destination, the operating system provides a default routing table entry, and this is called the default gateway, which contains the IP address of a router that can forward IP packets to their destinations. The network is the first thing we think about when we imagine computers getting hacked, right? And it's the pen tester's playground. It's both the first step and the final frontier of compromising a computer. It's also what makes of an entire building full of computers. It's fitting. Then we continue our journey with a discussion about compromising the network and using its own power and weaknesses to inform the pen test. The first step is getting on the network, and there are human, architectural, and protocol factors that make the mere presence of an attacker on the network potentially devastating. For this reason, defenders often deploy network access control (NAC) systems. The intent of these systems is to detect and prevent an intrusion on the network by identifying and authenticating devices on the network. In this section, we will review some of the methods employed by the NACs and demonstrate practical methods of bypassing these controls. Now, let's get started by the learning of bypassing media access control filtering and things to consider for the physical accessor. An attacker needs to be aware of the methods for the remote compromise: attacking the VPN, wireless infiltration from a distance using a high-gain antennas, and so on. However, pen tester can never forget the big picture. This is a field where it is very easy to get caught up and in the highly specific technical details and the misty human element of security design. There is a design flow concept that pen testers like to call the candy bar model. This simply refers to a network that is soft and crunchy on the outside but gooey on the inside. In other words, it's a model that emphasizes the threats of the outside world when designing the security architecture, while assuming that someone who is physically inside the company facilities has been vetted and therefore trusted. The mindset here dates back many years. In the earlier days of what became the internet, the physical access points to the network were inside highly secure facilities. Packets coming in over the network were safely assumed to be from a secure environment and sent by an authorized individual. In today's world, a packet hitting the border of a company's network could be from an authorized individual on a business trip, or it could be a very clever teenager on the other side of the planet, eager to try out some newly learned tricks. The candy bar model will come up in a later lectures when we discuss other network attacks. Once you crack the outer shell, you will often find that the path forward seems paved especially for you, and the successful compromise will inform your client of the devastating consequences of this mistaken assumption. Feel free to treat yourself to an actual candy bar upon successful compromise. You deserve it. How to social engineer your target is a subject for another section altogether, but for the purposes of this discussion, let's assume that you have a physical access to network drops. Not all the physical access is the same though, but if you convinced your target to hire you as a full-time employee, then you will have constant physical access, right? They will even hand you a computer. However, what's more likely is that you have exploited a small gap in their physical security stance, and your presence can be undetected or tolerated for only a short period of time. You have snuck in through the smoker's door after striking up some conversation with an unwitting employee, or you've been given permission to walk around for an hour with a convincing looking contractor uniform and clipboard. Or, which is my personal favorite, you earned trust and affection by bringing in a big box of donuts for the people expecting an auditor's visit based on a well-scripted phone call. And my client's still shaking after this test and will ask whether the donuts were real. And for now, we will demonstrate how to set up a Kali box to function as a rogue wireless access point while impersonating the media access control address of a voice over internet protocol phone. So you have found an unoccupied cubicle with an empty desk and a generic IP phone. So the phone is plugged in and working, so you know the network drop is active, and we will drop our small laptop running Kali here and continue the attack from the outside. Unplug the IP phone so that our bad guy can take the port, and we are then going to clone the MAC address of the IP phone on our Kali box Ethernet port. From the perspective of simple MAC address whitelisting methodology of NAC, this will look like the phone merely rebooted. So here I use ifconfig to bring up the interface configuration, but first let's actually increase the font size a little bit so you can see more better. Here now actually let's make here, and I also want to add the margins here, which is I think has to be somewhere here. If it's not, it's also okay. I think you can see clearly here. Yes. Terminal, yes. And here, this is our terminal margin, and we can make it like 50 pixel, and here. So now let's use the ifconfig here, ifconfig, and here you are seeing Gromit. Actually, let me open my Gromit here, and this is our marker which we're gonna use. And here, as you can see here, that in my example, my Ethernet port interface is called ETH0, and my wireless interface, which I don't have wireless interface right now, but if you have, it's gonna be called the WLAN here. Let me write it, WLAN 0, the first wireless card. And I will note this for later, as I will need to configure the system to run access point with a dynamic host configuration protocol, DHCP. and the domain name system, which is DNS. And here on the actual WLAN, which I will add my card later. And while running the network address translation through my Ethernet 0 interface, and I can use ifconfig here. Let's actually do this. So I can use the ifconfig the ETH0, which is my Ethernet card, HW Ether. So here I use this to change the physical address of the Ethernet interface. So I've sneaked a peek at the interface. So I've sneaked a peek at the label on the back of the IP phone, and the MAC address is here. See here, the MAC address is, as you can see here, lob slib sh ppp arcnet sit and so on. So actually this here if config ETH0 and Ether. And as you can see here, we got several informations here. This is hardware type, a list of possible hardware types. Here we have usages of how this works and so on. And let's now run the ifconfig command. And as you can see here, we have the Ethernet MAC address. So now let's bring the interface with this. So we're gonna use so we have to be the super user of the system to use this command. Now let's use the sudo s and enter your password. And here, as you can see here, we, instead of using Oxal account, which is a separate account, and this is our machine computer name, we came into the root account, which we are working on a directory of home Kali, but you actually learned this in lectures. So ifconfig ETH0, and here we are seeing our Ethernet MAC address, like inet address. This is a local netmask, broadcast, and so on. Now after that, we will use ifconfig ETH0 down. And here I will explain all of this later, but first let's write this config ETH0 w ether, and let's change our, as you can see here, our disconnected, we had the label disconnected from the internet, see here, but we will enable it. But now firstly HW ether, and we will enter our MAC address that we want to use, which in this case be something like AACCBB or something like 989221 and lastly 1A. And here after that we will enable our Ethernet 0 interface. So ifconfig ETH0 and up. As you can see here, our internet came live here. So now we will use ifconfig ETH0, and as you can see here, our MAC address is changed.